This is the Science Fair Microcomputer Trainer. It was sold here in the UK through Tandy stores, and in the US through Tandy's RadioShack retail stores. In this page from the RadioShack catalogue, we can see that the microcomputer trainer was new for 1985 and had a retail price of $29.95. It was around this time that the Science Fair sub-brand standardised its casing designs, moving from an eclectic mix of wood and various plastic styles into this new style with a cardboard base and blue plastic end caps. This material choice and standardisation was likely part of a cost reduction exercise, and the microcomputer trainer itself was a cost-reduced version of an existing product. The microcomputer trainer is a repackaging of Gakken's FX-Computer. This was originally released in Japan in 1981 and was available in English-speaking markets from at least 1982. I've shown this product in a previous video, and I'll provide a link to it in the description. If we turn the computer module over, we can see a Texas Instruments TMS 1100 chip. Here we can see it's marked with the value MP1312, and we'll see that again when we look at the chip on the Science Fair reproduction. As you can see, this chip is dated from 1982, week 27, and of course we'll see a later revision in the Science Fair version. The microcomputer trainer was available from 1985 until 1988, so had a relatively short production lifespan. As you can see, my microcomputer trainer is complete in box. There is a small dent in this area of the box here, but otherwise it's in fairly good condition considering it's over 40 years old. So let's take a look inside and take a closer look at the computer itself. As you can see, the microcomputer trainer comes with this comprehensive 180-page manual. And as you see on the front, the computer requires 6 AA batteries. If we flip the computer up and look underneath, we can see this unusual battery holder here, and these are where the 6 AA batteries are installed. There's no power switch on the computer, so the way you turn it on and off is by disconnecting and reconnecting the power wire just here, or removing the batteries from the underside. It's recommended to remove the batteries when the computer is not in use. The first thing the budding programmer would have to do is to connect the various components together using the pack of provided wires. This has already been done here, but as you can see in the user manual, the computer would have been provided without the wires pre-attached. As is common with the Science Fair Spring Terminal kits, there are various wiring diagrams that you have to follow. And it includes full point-to-point wiring numbers, so it's easy to connect all the required wires correctly. Unlike most of the Science Fair Spring Terminal kits, there is only one correct configuration for the wires in this kit, and once it's been correctly assembled, there's no need to change any of the wires with the possible exception of removing the power wire to disconnect the power. Unlike most Science Fair Spring Terminal kits, there is no schematic diagram of the circuit in the user manual. However, as there is only one correct configuration, you can see much of the schematic already laid out on the card casing here itself. To power on the device, I'm going to connect the final wire just here. The microcomputer trainer is aimed at ages 12 and above, and includes a number of built-in programs and games. These are documented in the user manual, and my favourite is game number 4, rat bashing. To run the program, all we have to do is reset the machine, press C to select the program, and then press Run. Once the program starts, it will ask us how fast we'd like it to go, and we provide a code 0, 4, 8, or C, and at that point the game will begin. So let's have a quick round of rat bashing. So we reset, we press C, and then we press Run. The computer is now waiting for a speed code. When we select one, the game will start. All we have to do is press the key matching the illuminated LED, which indicates which hole the rat is peeking out from. Let's start with speed code 0, the slowest speed. So I'm simply pressing the key that matches the rat hole. If I'm too slow, then no beep is heard. If I get the key wrong, again, no beep is heard. That time we got 7. We can restart the game now just by pressing the key here to run the game again. Again, we can choose our speed code. This time, let's choose speed 8. This time we only got 5. As you can see, on the faster speeds, the game is considerably harder. At this point, we can press reset to exit from the game and go back to normal programming mode. As I mentioned, the Science Fair Microcomputer Trainer is a cost-reduced repackaging of the Gakken FX-Computer from 1981. At the centre of the board here, we see the same TMS 1100 or 1100 CPU, and as you can see, it's marked MP1312, just as with the previous device. This one has a date code indicating 1984. While the chips contain the same ROM production code 1312, there are actually some very minor differences between the firmware on the two devices, and I verified this by downloading the ROM code from each of the chips individually. The modifications are fairly inconsequential. They actually improve the randomization of the rat bashing game that we've just played, so it's actually more challenging on the microcomputer trainer versus the FX computer, and it appears that there might be some additional code to try and improve the key debouncing on these Morse key style switches that we see on the Science Fair Microcomputer Trainer. Otherwise, the computing aspects of the two products are essentially identical. You can get a real feel for this by comparing the manuals from the two products. Here I have the instruction manual for the English language version of the Gakken FX-Computer. On the cover we see it contains instructions for 100 computer programs, and it's interesting that it uses the British English spelling of programs. But hiding just underneath, we have the Science Fair Microcomputer Trainer manual. And as you can see, they're approximately the same size and approximately the same volume. If we look inside, the content is indeed very similar. And other than a few differences to account for the differing form factor of the devices, the content is largely the same. If we look through here, we can see, for example, program number 11 is the use of the AIA, or add into A instruction, to add numbers together. We can see there's a program and a flowchart, as well as some instructions on how to key in the commands. If we now flip to the Science Fair manual and we look for program 11, we should see a very similar layout. Here we go, we have program number 11, the use of AIA to add numbers together, and again we see the same program, flowchart, and keying instructions. Of course, you can see these have been independently typeset, and in fact there are some minor differences between the text. I would surmise that these are probably independent translations of the original Japanese text. If you're interested, a scan of the original Japanese manual is available directly from Gakken online. As a cost-reduced repackaging of the device, there are some missing features in this particular iteration. The Gakken FX-Computer comes with this really nice reference card that provides details of the instruction set and a summary of what the command does, as well as direct page references to where in the manual you need to look to find out more information. It also includes details of the address and registers, and on the back it contains examples of how the execution flag or the conditional jumps work in the computer's programs. In the Science Fair version, this small table here serves as a substitute for that quick reference card, and as you can see, contains far less information. While I had been aware that the Science Fair Microcomputer Trainer was a repackaging of a Japanese product, I didn't realise that there was an official English translation for quite some time. However, having seen the Japanese language quick reference card, I was quite enthusiastic about getting an English equivalent for the Science Fair Microcomputer Trainer. To that end, I produced this Science Fair Microcomputer Trainer quick reference card. As you can see, it's styled very similarly to the Gakken examples. I have made some minor updates. Importantly, I've corrected some errors in the register details down here, as well as updated all the page references to ensure that you can find the correct cross-reference if you want to find out more information about any of the commands. On the rear of the card, I provide information about the flag status and the branch examples for the jump command, and by extension for the call instructions. I've extended the details on the bottom of the card just here to provide information about the various run modes that are available, as well as the built-in micro games. If you'd like your own copy of this card, I will provide a link to it in the video description where you can download and print your own. Another deficiency of this repackaging of the product is the lack of integration with any kind of electronic circuits. Despite the use of solderless spring terminals to connect the components together, Familiar to many of the Science Fair electronic kit products, this particular product has only one correct wired configuration, and there are no other electronic circuits you can build. In the Gakken version of the product, there is a secondary manual containing 65 electronics projects that you can study and complete. If we flip through, they start with some fairly basic electronic circuits, but as you go through the manual, they build up into more and more complex circuits that you can build and play with. While none of those circuits are designed to interface directly with the computer module, if we look again at the FX Computer's main instruction manual and we flip through, we should be able to find some circuits here at the end of the manual that talk about the use of the call input instruction, and this allows us to wire up certain circuits following diagrams here and interface them with the computer module itself. There are actually only 2 of these circuits and programs detailed in the instruction manual. However, they are entirely missing from the Science Fair Microcomputer Trainer version of the instruction book. The call input instruction is instruction E3, and if we look down this instruction summary table just here, we see that E3 is marked as not used. However, as I've already mentioned, the firmware embedded in the microprocessor is actually essentially identical between the 2 versions of the device, and the E3 instruction is still present and can be used. To facilitate the use of the call input command, I went ahead and created this version of Appendix B. This provides details of the call input command and provides some suggestions for circuits you might want to use to get some basic input into the Science Fair Microcomputer Trainer. Now, again, as with the quick reference card, I created this without any knowledge of an English translation. And unfortunately, Gakken excludes the relevant pages from the available download of the Japanese language manual, so this instruction was entirely speculative. The first external input circuit, designed here, was actually copied from some reverse engineering by a Japanese user, which I had translated. And again, I will provide links to the relevant pages on the web in the video description. This is essentially the official circuit that is described in the English language translation of the Japanese original product. There we use an NPN transistor and a couple of resistors to allow us to provide inputs. In the original, there is actually 100 ohm resistor just here. I have swapped it out to a 220 as it is a more standard value and works equally well. I also devised an alternative external input circuit which provides an improved way of providing external input. If you use the first circuit, there are limitations on using the keyboard input and the external input at the same time, although using the second circuit alleviates that issue. It's also slightly simpler, requiring just 2 diodes and 2 inputs, whereas the original requires 3 inputs. I also provide an example program here, and this program and flowchart allows you to detect the value of a external input when a key is pressed. As it mentions, this requires the second circuit because the keyboard will interact with the input command otherwise, and that can be problematic. There's also some detail on how the K port, the various inputs available, work and how you can use them to provide input. Now, the fact that RadioShack didn't provide any kind of detail on how you would connect the microcomputer trainer to an external circuit seems like a big oversight, especially with the spring terminal form factor. As we've already seen with this page from the RadioShack catalogue, there were a variety of spring terminal electronic project kits that could potentially be interfaced with the Science Fair Microcomputer Trainer with appropriate hardware and wiring. And as it happens, I do indeed own one of these 13-in-1 project kits contemporary with the Science Fair Microcomputer Trainer. Here is my boxed edition of the Science Fair 13-in-1 Electronic Project Lab. It's a particularly long-lived example of a spring terminal kit from Science Fair and RadioShack. It was available from 1983 all the way through to 1998. And here is the product out of the box. As you can see, although it's a fair bit smaller, it does have a very similar design language. So let's set them up side by side and see if we can work out how to connect them together. If we look again at my Appendix B for use with the call input command, we can see there are 2 potential circuits that we can use to connect external input to the Science Fair Microcomputer Trainer. While the second circuit grants more flexibility by allowing you to read the external input and the keyboard at the same time, the first circuit most closely approximates the design provided by Gakken in the Japanese and English translations. Additionally, in this circumstance, it is our only practical option. As you can see, the second circuit requires 2 diodes, and the 13-in-1 electronic projects lab contains only 1. We will have to make some minor modifications to the first circuit to make it work with the 13-in-1 electronic projects lab. Fortunately, both of the provided transistors are of the NPN type and so are suitable for our particular application. However, there is neither a 4.7K or 220 ohm resistor in the electronic projects lab. I've already wired up the core of this circuit here by using the substitutes of 5.6K for the 4.7K resistor and the 680 ohm resistor in place of the 220 marked in the diagram here. These values will be perfectly adequate for our purposes. Next, we need to make these connections here to provide power and signaling from the microcomputer trainer to the electronic projects lab. First, I'm going to connect some wires to the required connection points on the electronic projects lab. Now we can connect ground to position 39, VCC to position 28, and the 07 signal to position 45. As we only have one key switch, we're going to connect that to K1, which is position 40. So that completes the wiring that we need for the first circuit here. If we try and use the external input at this time, we'll end up registering spurious keyboard input. The reason for this interaction is the fact that the first circuit only avoids interrupting the keyboard scan when it's dealing with the final column of keys, the address set, increment, run, and reset buttons. However, if we can ensure that we never have external input if we're trying to read from the keyboard, or our program never tries to read from the keyboard, then this first circuit will be entirely adequate. Of course, to do something meaningful with that external input, we now need to write a program. I have a suitable program here for reading from the external input. I'm going to enter it into the computer now, and I'll fast forward through that part of the video for you. But if you'd like to learn more about how to program the Science Fair Microcomputer Trainer, I'd encourage you to watch the FX-Computer video that I've also created. As the two products are functionally identical, the programming of the two devices is essentially the same. So I've now finished entering the program. All we have to do to run the program is to reset the machine, and this brings us back to address 0, and then we can set the run mode, which we're going to use normal run mode, which is run mode 1, and then we're going to press the run key. As you can see, we now have a 0 on the hex LED display. This program keeps a running sum of all of the external inputs. Every time we press the key on the electronic project lab, we would expect the display here to increment by 1. So let's give it a go. As you can see, every time I press the key, the display goes up by 1. To prevent double counting, the display only updates once I release the key. So let's take a look at the flowchart to see how the program works. First, we store a 0 in the A register. This is the first value that we will display. It also stores that value from the A register into the memory. Normally, you would set the memory address location by setting the Y register. In my case, I really don't care where in memory that is, and I don't modify the Y register throughout the rest of the program, so it doesn't really matter what that value is currently set to. However, it is good practice to specify the Y register when using the microcomputer trainer. At this point, we go ahead and we store the AR, the A register, into the output register, which ends up being displayed on the hexadecimal display using the output command. We then go ahead and use the E3 command, the call input. This gets an external input and stores it into the A register. This is why we needed to store the A register into memory. Here we use a little trick to determine whether or not we've read anything from the external input. We do this by adding F to the A register. If the A register contains anything other than a 0, adding an F will result in a carry in a 4-bit system. A carry sets the flag. If there's no carry, we skip the jump instruction, and instead we move ahead to this instruction here, which restores the A register from memory. Then we follow this unconditional jump along to instruction 3, where we redisplay the A register on the display before going through the input stage again. If on this occasion we do then have a carry, we do follow that jump instruction and we go down here to OF. At this stage we know there must have been something in the A register, but we've changed it by adding F. In a 4-bit system, adding F is essentially the same as subtracting 1. So to get back to where we were, we just need to add 1 again to the register. At this point we have the original value we read from the external input in the A register, and we want to combine it with the backed up value we stored in memory. We use this instruction here to combine the memory with the value in the A register and store that back into the A register. We then need to make sure that value is stored back into memory. Now we need to wait until the external input is complete, and in our case that means the key has been released. To do so we need to call the call input routine once again. We do so here, and again we use the overflow trick to determine whether or not we've read anything from the external input. In this case, if we have a carry, we actually want to loop around and keep reading until we make sure that value has cleared. Once it has cleared, that means all of the external inputs have released. At that stage, we need to restore from memory the value of the A register, and then we can loop back around again using this unconditional jump back to instruction 3, where we display the A register on the external hex LED. You might have noticed that in the program, I'm very careful to ensure I preserve the value that was read from the external input. I'm not just counting whether or not external input's happening, I'm trying to determine the exact value that was provided. That's because the call input routine will actually read a 4-bit value between 0 and F when presented on the K inputs, K1, K2, K4 and K8. Here I've connected the key switch to input K1, and that's why when we press a key, we see an increment of 1. This means I could move our external key switch from the input K1 to the input K2, and this should result in an increment of 2. So let's move the wire over and see if it works. As you can see, we now count only even numbers. Of course, the same is true for K4 and K8, so let's give those a go as well. So, as you can see, it's fairly easy and practical to get external input from an electronic projects lab into the Science Fair Microcomputer Trainer. The fact that Science Fair failed to present this as an option really seems like a bit of an oversight in the marketing strategy. While the 30-in-1 Electronic Projects Lab was a mainstay of the catalogue for 15 years, being listed from 1983 to 1998, the Science Fair Microcomputer Trainer only survived between 1985 and 1988. Encouraging people to combine the different kits surely would have boosted sales. Of course, part of that will be the fact that the microcomputer trainer was late to market. By 1985, several low-cost home computers were available in the global marketplace. Here in the UK, Sinclair had been depressing the prices of home computers, and equally a price war by Commodore in the US had significantly reduced the cost of home computing. This meant that microcomputer trainers were only of interest to hardcore enthusiasts, and even they might have preferred a more fully featured system such as the Commodore or Sinclair machines. Without the ability to easily extend the system, the microcomputer trainer is quite limited. However, it does give the user the ability to really learn the fundamentals of very low-level assembly language programming. As such, it is one of my favourite items in my collection. But I think that's all I have time for to talk about today. So I hope you found this video about the Tandy Radio Shack Science Fair Microcomputer Trainer interesting, and I hope to speak to you again soon in the next video.